before we get started, now if you know from our pre-class banter, don't answer. One of these three people has a birthday today. Which one? Okay, it's this one here. So who is your classmate who has a birthday? It's Jonathan's birthday. This is what? Natalie, who took physics 2 years ago, and it's Ann, right? Yeah. It's been a while, so Ann. Who took physics like the year before her? No, it's Anna. And okay, well, it was Ann B-R-E, I don't know. Who took it with Natalie? Natalie's friend. Okay, so just wanted to wish him a happy birthday, the young lad of 18. So he can vote now. Okay, before we actually start, I did, during the test, put a note up here just a couple weeks, I should have said something earlier. A couple weeks ago, a student who, I don't even know what her major is, was asking about, should I go to Rosario Beach to take a class there? Because I just want to, get some more diversity and whatnot in her biology. And I said, well, you should totally look into the REUs. The REUs are research experience for undergraduates. And the thing about the REUs is they pay you. They pay you what I've seen is typically around $4,000 a month to go and do research and take classes. Plus they cover your room and board and expenses for travel. So it's a really great experience. You have to be the summer between your sophomore, junior, or junior and senior year to do these, which is where most of you fall. And most of them have a deadline that's like February 1. So I'm too late for most of them, but after I put that on the board, one student, went looking and found one that's within an hour's drive of his home and has a closing date for applications of March 1 and is applying. It's really a good program if you can get into it. Now, the odds of getting in aren't super high, but there are lots of them, which helps to dilute it and make it so you have a better chance. And so if you're interested, just look online for REUs. These are sponsored by the federal government, specifically by the National Science Foundation, the NSF. So the NSF has a website that allows you to sort through and find ones in the area that you're interested in, and then application details. And starting next year, I'm going to be a little more letting people know like in October-ish so they can plan and have a better chance of getting in. So I just want to, we want the sharp minds to take advantage of these. And you know where the sharp minds are at Union College? They're in this classroom. And so I want you guys to try to take advantage of these if you have the ability or the time. All right, that said, it is time to move on with physics. Only 3 minutes of time spent. So let's start with a question to make sure we understood from last class period. Which statements, so this has multiple answers, you put in all the ones you believe are correct and then hit enter, are true about electric and magnetic forces on an electric charge? Okay, I'll give it about 5 more seconds. Okay, so our answers were 2, 15, 9, 6, and 15. All right. Well, we had 2 answers with 15, which is a majority. And so I'm not going to have you discuss them. I'm just going to go straight to Nate. Nate, which did you choose? And give us your reason.
I chose B and D.
Okay, Nate chose B and which one?
D.
D as in dog?
I chose B because the stronger the charge, the stronger the electric force on the charge.
Well, what's the equation for, do you remember the equations for each?
I think KQ1 and Q2.
Well, what's the force for on due to an electric charge? What's the force on an electric charge due to an electric field?
KQ.
That would be between point charges. Okay, Q1, Q2 over R squared is between point charges. But for electric field, a charge in electric field, it's the simpler form. Don't know offhand. And you don't have to have the equations memorized. Everyone realizes that, right? So the equation for the electric force is QE. And so you're right. That is proportional to charge. And then what's the equation for the force due to magnetism? More recent. Do you remember that one? No. Okay, that's Q V vector cross B vector. So that also is dependent on charge. So B was definitely correct. You also answered both forces are perpendicular to the field. But if we look at the direction of the electric force, it's parallel to the field. So it can't be D because the electric field is parallel to the force instead of perpendicular. Now let's just start at the top. The other answer is A. Both forces are proportional to speed. Do you see speed in both equations? So it can't be that because there's no speed in the electric force. C. Both forces are parallel to the field. Okay. Why do you say no, Carrie?
Because the magnetic force is proportional to the cross product, which is perpendicular to the field.
So it's perpendicular to both V and B, which means it's not parallel. Good call there. And then we're left with the last one. Both forces are proportional to the field strength. They both have the E's there, or the E and the B. So the correct answers were those two, the ones that had the majority. Okay, now I went through this yesterday, and I'm going to go through it really quickly today. If we want a charge to go straight through both an electric and magnetic field without speeding up or slowing down, then we're going to need to have the electric field and the magnetic field perpendicular to each other so that we can make the forces in opposite directions. So the first line here is just straight what it means to have a net force. The net force is the electric force plus the magnetic force. No shocker. If we're in equilibrium, the net force is equal to 0. So this is saying if equilibrium, then we have it 0, and the force electric is QE, the force magnetic is QV cross B. And so if I take those two equations, you notice I have Q in both of them. Come on. And so I can cancel the Q's in each equation and then just solve for electric field has to be equal to minus V cross B. What's a more convenient way of writing minus V cross B?
V cross B.
Yeah. If you reverse the order in a cross product, you change the sign. So that's a more convenient way of writing it. Now, if the net force is 0, if the velocity is perpendicular to the magnetic field, then the magnitude of V cross B is going to be V times B. And so we should have the magnitude of the electric field So writing this without vector signs, the magnitude of the electric field should be equal to the magnitude of the magnetic field times the magnitude of the velocity, which then solves to the speed has to be E over B. So that's this equation here. If it's going to be in equilibrium going through cross electric magnetic fields, the speed has to be that specific speed. If it goes too fast, the magnetic field is going to be stronger than the electric field. If it goes too slow, the magnetic field is going to be weaker than the force from the electric field. And then finally, using the rules for cross products, this cross this is this. The easy way to get this actually is to make the analogy a right-hand coordinate system. You guys have heard me say right-hand coordinate system, right? Because you can draw your X, Y, and Z axes many ways. But a right-hand coordinate system is made such that X cross Y is equal to Z. That's why we define a right-hand coordinate system, because X cross Y is equal to Z. But if we just rotate, we could do Y cross Z is equal to X, right? The directions follow if you just shift it over one and keep the same order. And so if I take my relationship E equals B cross V, the directions still work, the numbers don't, but the directions still work with E cross B equals V. So this is only for directions. So the velocity's direction has to be in the direction of E cross B for you to have equilibrium. So I'm going to erase this because it's only for direction. And if I leave it there, somebody might say, oh, well then E cross B must be V because he wrote it on the slide. And it's only direction that's true. So you have a specific direction the velocity has to have, a specific velocity that it has to have for a charged particle to travel in equilibrium in cross electric and magnetic fields. So here's an example of how we use that first selector. It says an ion source, like let's say a radioactive sample. We're going back to the time of Rutherford. And so we just have this little radioactive sample and we put a little barrel on it so they come out in one direction. And then we go through electric field. Notice the electric field is going top to bottom. And we go through magnetic field that's going down. And the particles get deflected. If they're going too slow, they go one direction. If they're going too fast, they go the other. What if one's a positive charge and another one's a negative charge? What if one's an alpha and one's a beta, for instance? Alphas are positive, betas are negative. What difference does that make here? They would have opposite forces, but if we're in equilibrium, if they're at the right speed, it'll still go in a straight line. So it's still going to be a perfect speed selector, whether it's a positive charge or a negative charge. If it's doubly ionized, it'll still be a perfect speed selector. And so we just select the speed, and then we use a mass spectrometer, which in this case is just a magnetic field, to make them deviate and measure how much they curled. And in this case, since they all bent upward and it's a downward field, what direction is the magnetic force in these particles? For curled upward, what direction is the magnetic force? It's going to accelerate in the direction of the force, so to the left. To the left is best because as you move around, it's changing, right? But to the left, that's still to the left. So if we have a particle that has its V going forward, and its force is going to the left, V cross B, yeah. We have like that. Is that a positive or negative charge? We have V cross B is in the direction of F. Is that positive or negative charge? Positive. What would happen if it was negative? It's in the opposite direction, so negative charge would occur down here. So this is only looking at positive ions in their mass spec picture. For time, I'm going to skip over. This is how you actually do your voltage or your speed selection. You go through a voltage difference, delta V, and then 1/2 mv squared is equal to minus q delta V, and you get the speed. And so this leads us to a very important experiment done by Thomson. Thomson was studying what were called cathode rays. it was discovered that if you have as well as they could evacuate back then, vacuum tube, and you have a cathode and an anode, positive and negative terminals, you would actually have a beam of particles that comes out of the negative one. And I still can't for the life of me figure out why the negative one is the cathode, right? Because cat means positive, right? But they had this beam of particles coming out. Now, at first they didn't know what it was. But with careful study, they found that it could be deviated with a magnet. If it can be deviated with a magnet, then it must have an electric charge, because you don't have a force due to magnetism unless you have an electric charge. And so with that electric charge, then they also could put in an electric field and see a deviation electric field. So they were able to then, by crossing the electric field and magnetic field, determine its speed, and further experiments actually identified that these cathode rays were electrons. So when they were first discovered, they didn't know what they were, but later, after they did the testing, they realized that you had electrons that were coming out of that cathode. I put this in here because a lot of people here are interested in medicine. And one of the cool things you can do now, I imagine that you have to cut down to get to a vein or artery to do this, but you can measure the blood flow without actually cutting the artery. You have an artery there, and you put it in a magnetic field. And if you have ions flowing through your blood, which you should, when those ions go through that magnetic field, they're going to have a force such that positive charges go one direction, negative charges go the other. But of course, the charges can't escape. They're stuck in that blood vessel or artery. And so you start building up a positive charge on one side and a negative charge on the other. And if you measure the voltage difference, it'll tell you how fast the blood is flowing, because you have a force that is making the charges move up and down. But as you build up a positive charge on top and a negative charge on the bottom, you're building up an electric field, which is going to make a force to try to keep the positives from going where the positive is. And so when you reach equilibrium, you'll have the net force on those particles moving through is equal to 0. And so when you reach equilibrium, you know what your electric field is by measuring the voltage and knowing what the diameter of the artery is. So you know the electric field, and you're controlling the magnetic field, so you know the magnetic field, and you can determine what the speed of the blood particles are, the things moving in the blood. So it's a cool, like I said, you don't have to cut the artery, but I mean, unless you have a vein or an artery that's, visible and that you can attach to right here, it's not going to very much work without cutting down. But it's cool, right? Don't have to cut the artery to measure the current. I think it's cool. That leads us to something called the Hall effect. The Hall effect, named for a dude whose last name was Hall, don't remember his first name, is that same idea. We can have a piece, and these pieces of material are usually something made out of a semiconductor like silicon or germanium. Semiconductor, almost fit. And you put current through that, and I'm going to the problem, I'm not going to do the problem. You put current through it, you put it in a magnetic field, and you measure the voltage difference, and just like what we did before, you can determine how fast the particles are going. Now, how these are actually usually used is to measure magnetic field strength. What you do is you take a silicon wafer and you know its properties, and you put a known current through, and you measure the voltage difference that's produced. And that voltage difference then will be proportional to the strength of the magnetic field that is perpendicular to the velocity and the electric field. And so you can put it like this and measure the magnetic field one direction like this, measure another direction like this, and measure it the third direction and get the total magnetic field. So it's called the Hall effect probe. Now to the new material. That stuff was stuff I wanted to cover last class period. So I lectured, which would be Friday. This here is the new stuff. We've learned the force on a charged particle is QV cross B. And we know how to use the right-hand rule. We know its magnitude is QVB times sine of the angle between V and B. What if I have a wire with lots of charge going through it? If I have a wire with lots of charge going through it, I'm going to have a whole bunch of charge carriers. What's the charge carriers in a wire? What's moving in a wire? Electrons. Okay, so we have these electrons. How fast are the electrons traveling? Slower than that. They're traveling typically on the order of around 5 to 10 centimeters per second. Not very fast. Is that surprising? It should be. Because if I flip off the light switch, how long does it take for the lights to go out? Pretty much instant, right? As well as we can tell. If they're only going like 5 centimeters per second, you think about the length of the wire going from this switch to there, and you think, it should have taken many seconds. But it's like instant. The reason is, well, there's two reasons. Number one is, the wires are themselves waveguides. They're guiding what we call electromagnetic waves around the outside. And those electromagnetic waves are creating electric fields that are dragging charge. So the charge is being dragged by the wave, not just charge going through. We think of it like water in a hose. But of course, when you turn on the water in the hose, the second thing is, if the hose starts filled with water and you turn on the faucet, how long does it take for the water to come out the other side? If it started filled, it takes virtually no time, right? Because you have a chain reaction. This water molecule pushes that one, pushes that one, pushes that one. And the chain reaction makes it come out the end almost instantly. It probably would have been better if I said you have the water flowing, and you're holding it up like this, and then you turn it off. It stops instantly. That's easier to see because it's already filled. That's what's going on essentially with the wires. You have chain reaction, so one electron moves here, the next one moves, the next one moves, the next one moves. And even though they're moving really slowly, the chain reaction goes very quickly. What's a good analogy to that? Traffic. You are at a stoplight, everybody stopped. The light turns green. You have a chain reaction. The first car leaves, second car leaves, third car leaves, right? Come to the next light, the light turns red, first car stops, second one, and it backs up. Or you watch traffic jam, you have these chain reaction things. And the speed of the chain reaction is much faster than the speed that any car is moving. Right? When the light turns green, the car that's fifth in line does not start instantly, but the time from when the first car starts to when they start is much less than the time it takes them to drive from that position to the starting position. Right? So the chain reaction is going much quicker than the cars. So the same is true for the signal going through wires. And so this here is saying the charge that's traveling through a wire is equal to N, the number of charge carriers, multiplied by, and they change the meaning of Q here, the charge of a charge carrier. What is a charge carrier in a normal wire? I asked you 3 minutes ago. It's an electron. So this Q is equal to minus the charge of an electron. Why minus? Because when you put E, it always is a positive number. So that Q is minus E, and N is the number of electrons. Now we define current as, what's this lowercase n? Lowercase n is the number of electrons or charge carriers per unit volume. So it's a charge density. Different types of materials have different charge density. Now the charge density is only the charge that can conduct. So if you have iron, you have some electrons that are bound to each atom. Those aren't part of these electrons. Only the electrons that are free to move are counted. And it depends, iron's going to have a different electron density than copper or than nickel. So each one has its own different electron density, but it depends on your material. It's a material property. Q is the charge of the charge carrier, like I said. A is going to be the cross-sectional area of the wire. And of course, V sub D, we call that the drift velocity. That's how fast, on average, your charge carriers are moving down the wire. Now, I don't have a picture for this, but in a typical wire, if there is no voltage difference across the wire, are the electrons moving? What do you think? The answer is yes. Electron will go bling, 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 bling. It'll bounce around. It's moving. But why you were saying no is, what's its average velocity? 0. So the V drift equals 0 because the V drift is the average velocity of the electron when there's no voltage on it. Now, when there is a voltage, it's going to start moving. So when you put a voltage on it, it's going to be going ding, 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 ding. But it has a general motion that is now drifting. Now I put arrows. Those arrows, of course, this one here is not the direction it was moving at that point. But it has a drift velocity now. It's still moving back and forth, but the average velocity is in one direction. So that's what the drift velocity is measuring, the average speed at which the electron is making its way down the wire. So current is the charge density times the charge of the charge carrier times the area of the wire times the drift velocity. And so you look at that and you're like, well, I think I can make a substitution here. Since capital N is the number of charge carriers and lowercase n is the number of charge carriers per volume, then capital N is just equal to lowercase n times the length times the area, because the volume is going to be length times area. And so putting that in, I can rewrite my force equation like this. Notice we have N, Q, A, VD. But there is one difference. What's that one difference? One's a vector VD and one's not a vector VD. And this is something that is a nuisance to me. It annoys me, but it's a simple, because of the structure of the math, fact. Current is not a vector. We can't substitute this because current doesn't have a direction. Now, when I say that, I feel like I am a lying sack of feces. Because if I have charge moving through a wire, there's a direction that it's moving. Doesn't that make it a vector? Right? Vector has magnitude and direction. It had a direction, it had a magnitude. But it's the mathematical buildup. Charge density or current density is a vector, and the current is not. The current is the integral of charge density dot dv vector, I think it is. And so that's why it becomes a scalar. And so because of that, we have to say, okay, well, something's got to be a vector. And so we're just going to say L, the length of the wire in the direction that the current is flowing, is what we call the vector. Once again, how stupid do I feel saying that L is in the direction of the current when the current doesn't have a direction according to what I just said? It sounds wrong. And so we can replace this whole thing, that was everything here, with current times our length vector. And so then we write our force equation as the magnetic force is equal to IL cross B. So the force on a wire carrying a current, after all of that work, comes out to be that the force is the current going through the wire times the length of the wire crossed with the magnetic field. Question?
So in the first semester we talked about vectors,
Yeah.
And what's not a vector if it like goes around in a loop and it ends where it started.
Well, that's a displacement of zero.
Okay. So
It's not a vector, it's a displacement of zero.
So for current, it's not a vector because,
For current, it's not a vector because we define current as an integral of the dot product. An integral of the dot product, well, a dot product always gives you a scalar. And so it's because of that definition. And, it's kind of uncomfortable to me. But I have to at least give the reason. Actually, I usually do kind of gloss over. I usually don't go through that and just say, current's going this way. And as I said, this here, I still write it like this because I know the direction of the current. And since the direction of the L vector was the direction the current is going, I like to write it that way, but technically the equation I circled, the right-hand half, is technically wrong, but it's practically easier to use. So Li cross B, where L is the length of the wire, I is the current going in the direction that the current is going, and B is the magnetic field. So we've already worked some problems with magnetic force. Now we have new ones we can work on. Force on a wire that has current going through it in the presence of a magnetic field. So when you're working with a wire with current through it and you want to find the force due to magnetism, you have, just like before, the magnetic force is going to be 0 if the current is 0. Well, that's clear, right? Since you had, well, it's written down below, I guess. But force equals, I'll write it the technically correct way, Li cross B. So if I is 0, of course it's going to be 0. If the wire is parallel to the magnetic field, then L cross B is 0 because the cross product is only multiplying the perpendicular parts. If you ever get confused between a cross product and dot product, remember the cross has two perpendicular lines. It's the perpendicular part, the two perpendicular lines. So if the wire is parallel to the magnetic field, or of course if the magnetic field is 0, then you again would have a magnetic force of 0. I think no one's going to get tripped up on the current being 0 or the magnetic field being 0, meaning no force. But that direction is one that can trip you up. You have to pay attention to the directions. Okay, moving on. Otherwise, determine the angle L and B, and then use this equation here to find the magnitude, and the right-hand rule to find the direction. So just like I've been advising for basically this semester, do the directions separately from the magnitude. So let's do a practical problem. Get some experience. A 125 meter long power line is horizontal and it's running north-south, carries a current of 2,500 amps toward the south. So our picture here shows north and south, and it shows the current, and its value is 2,500 amps. Magnetic field is 0.052 milliteslas. It's pointing north and inclined 62 degrees below the horizontal. What's the magnetic force? So let's start. Number 1 on that list was conditions that give us 0. Condition number 1 to give us 0 was, is the current 0? Is the current 0? No. Condition number 3 was, if the magnetic field is 0. Is the magnetic field 0? No. Right, those two that I don't expect anyone to ever get confused. Then we have the middle one. Is the magnetic field parallel to the current? No. So that means it's not going to be 0. Even though if you looked at the words, you're like, well, it said north here, south here, north and south are anti-parallel, which would still give you 0. But it's not going north, it's 62 degrees below. So now we do the next thing. What's the angle between my current and my magnetic field? Now, technically, it's 180 degrees minus 62 degrees. Which is equal to, is that 18?
118.
118, yeah, whoops. 118 degrees. I said technically because we have the force is equal to ILB sine of theta. Sine of 118 degrees is exactly the same as sine of 62 degrees. So you would have been just fine using the 62 degrees because sine of 118 degrees equals, oh, crud me, messing up. Because they're equidistant from 9 degrees. So we put in our numbers. Current is 2,500 amps. The length is 125 meters. Magnetic field is 0.052 times 10 to the minus 3 Teslas. And then we have sine of 118 degrees. So what do we get for that force? How much? 14.3 newtons. Just make sure there's not times 10 to the something. Okay, so we get the strength of the force, 14.3 newtons. Is that measurable? Is that something you could determine? I mean, yeah, that's a reasonable force to measure. What direction is it pointing? Okay, I have an answer. The answer was east. Let's see if that's correct. So we have IL or LI. Whichever way you do it, your index finger has to point that way. And then I need to orient my hand so I can make my middle finger point in the direction of B. So I need to orient my hand so my middle finger can point down and back. My thumb is pointing out of the board. So if north is here and south is here, should be, actually, if you look down from above, I have to look down from above here in my, yeah, north, south. Looking down from above, it goes like that. And so my index finger was pointing that direction, and my middle finger was pointing down in that way. Yeah, east. Getting these pictures straight is not overly simple. Okay, so that's an example of how we find the force in a wire due to charge going through it. It's not really much different than what we did before, QV cross B. It's just different variables. So let's look at a more complicated situation. What direction is the net force on this loop? So this loop, it's fixed on an axis that's stationary there. And we have the forces due to current going through. Do I have the current the right direction? Yes. Current going through the loop as indicated with the arrows. And just to make it clear, this direction is up. This direction here is into the screen. This direction is out. Obviously down, right, left. Actually, to make it all match. Yeah, 8 answers so far. Okay, I'll get about 5 more seconds. Okay, so our answers here were okay, no majority. Discuss with the people around you what you answered and your reasoning.
Those have to work, but it's like the net force on the whole unit is 0. Right. So you can like do the current static situation, it's like on the whole loop, there's no
Yeah, no,
any
that's not
difference.
really what you're saying. Current is going the same direction as the right, but it's still when it's on like F three, I don't know, F1 or F3, but that's your, and then the other way, straight opposite. So there's still no parallel.
I think the first one you did, so you were still. Okay, so now I understand what's going on.
Yeah.
This way. Yeah.
It's been saying you're not answering.
Why do you ever choose to?
Yeah, like they are for that one for the current going.
I think it's because the first one had the answer on. The first one had the answer on.
Oh, yeah.
You do that to me all the time.
Okay, let's try this again. Now I got one from both of you. Good. I was wondering why you guys weren't answering, like you were ignoring me. Okay, Isaac and Caitlin. Caitlin MacArthur.
Did you reset it? Oh, yeah.
Okay, there we go. Okay, this time around, we had a very different set of answers. Okay, so Brandy, what's your answer?
Well, we kind of said there's a force going up and one going down, and as the current goes around, the force is going to be changing, so it's going to be perpendicular and then parallel to the field as it goes around. So it's going to be zero at some point.
Okay, your answer is right. It's going to be zero because if we look at this, let's look at each piece of the wire individually. Now I'm going to stick with Brandy here. What can you tell me about the force on wire 1, which is the piece right here?
It's going to the right.
Okay, well, the current is going to the right. And the magnetic field, what direction is the magnetic field going?
To the right.
To the right, yeah. It's kind of hard. Let me zoom in. That arrow there shows it's going to the right. So we have the current and the magnetic field in the same direction. In that case, what does that tell us about the force? Has to be zero. So force 1 is 0 because I1 is parallel to B. Okay, now I'll move on to the birthday boy. What direction is the force 2? It shows you, but tell us why.
It's down because current is going in, magnetic field is to the right. Right-hand side.
So yeah, current is in, magnetic field is down, or is that way, right? Your thumb points down. And what's its magnitude? You might notice here that it's very hard to read, especially because my arrow's over it, but that's a distance A.
So IBA sine beta.
What's the sine of 90 degrees? 1. So we just put IBA. Okay. Actually, I skipped Gila. F3 Gila. So that's looking up there. What's the force on this right here? Okay, your current is going to the left. What direction is magnetic field? And what does that make your force? No. You have this one's to the left, this one's to the right. 0. Right, it's 0. Because I is anti-parallel. I'm still going to put the parallel sign, but it's actually anti-parallel because they're going like that. I don't know one, so I know the sign for not parallel, but that's not going to help me. Finally, now we get to Hannah. Tell me about force 4 here. I know it's got an arrow, but explain it.
It's going up.
Because.
I don't know.
Okay, Katie, can you help her out? Because of this. Okay, which one is your index finger, Katie?
Index should be current coming out towards us,
Okay, so the index finger is going to be current coming out toward you.
and then our magnetic is headed right,
Okay,
and then
makes your thumb point up. And so what's the magnitude going to be? I forgot to write the direction of that one. IB, what was the other one? Well, what was the length of that piece? It's marked here. I circled it A. And this one is up. So there's our 4 forces. When we add these all together, it gives me 0. So the net force was 0. Now this is the design for an electric motor. It has a net force of 0. How is it going to do me any darn good? It's not the net force, it's the torque. Because we don't want our motor to go cruising down the road. What do we want our motor to do? We want it to rotate, and then we use that rotational energy to make our car move down the road if we are so lucky as to have, a Tesla or, something like that. None of us are probably so lucky. So, actually, before we do this, let's calculate the torques. So that was the forces. Let's do the torques in red. What torque would we get from force 1? 0. Really tough. Okay, going to Isaac now, the next person who didn't have to answer a question. What torque am I going to get for force 2? Now, the torque needs to be about this axis. Do you remember the torque equation? Because if you don't remember, then it's useless to go further.
Yeah, I don't know.
Okay. What's the torque? Dude, last semester? Okay, so torque is a vector is equal to R cross F. Another cross product. We've already learned this one. That's where we learn cross products. So R is the distance from the axis to where the force acts. So look at our picture. That's the distance from here to here. That's R. So how big is R? 1/2 B. So that's going to be equal to 1/2 B in magnitude. The direction is to the right, so I guess I should put the direction in here. Cross to the force, and the force we learned was IB, yes, A. IBA, and this one here was down. So right and down, what's the angle between right and down? 9 degrees. So if we have 9 degrees, they're perpendicular. We're multiplying perpendicular components, so that's going to be times sine of 9 degrees times 1. So it's going to be equal to 1/2 IB, AB, and then we need a direction. So how do we find the direction for a cross product? Index finger goes in the direction of which variable? The radius, because it's the first one. So index finger is going to point that direction, middle finger points down, thumb points in the out direction. So that's torque 2. Torque 3 is again going to be 0 because the force 3 is 0. Torque 3 is 0. And last of all, Aaron, what is torque 4 going to be?
1/2 A B or IB A B. And then I didn't understand why was the last one out?
Okay. Because using my right hand rule. Oh wait, I did it backward. It's in. Good call, Aaron.
This one's out.
And this one's out. So if we add these together, actually this one here is also in. It's also in because we have the radius is opposite direction and the force is opposite direction. So they're both in, and so the total torque is equal to IBAB in the in direction, which is IB times the area in the in direction. And that's what's going to make our motor rotate. I had to finish that. Well, the time ends now anyway. So
So if we make it a bigger motor, more torque.
if it's a bigger area, it's going to have more torque. That's right.